This is 2763. It is about an oceanographer, and the oceanographer wants to measure the resistivity of water as a function of depth, because salt water, ocean water, has lots of ions in it. It's very salty, and those ions affect the resistivity of the water. So if you measure the resistivity, you can measure properties of the water, how much organic material's in it, things like that. So that's what she's doing. So she's built a device to do this. It's basically two concentric cylindrical cylinders made out of metal. And when you immerse those in water, you get water between the cylinders, you apply a voltage between them, and you get a current. Measure the current, and you can get the resistivity. So that's what we're going to calculate. So I'm actually going to draw this in cross-section. It's much better to draw these in cross-section than to try some 3D drawing. And just to simplify the drawing, I'm actually going to make the central cylinder solid. It actually doesn't matter if it's a cylinder, it can just be a solid rod. So here is a solid metal cylinder. And we know that the radius to the surface that touches the water is RA. And then outside of that is another cylinder. Looks something like this. Oh, goodness. Let's assume she's a good machinist and didn't make it look like that. There we go. So this one is another metal cylinder. But remember, this has cylindrical symmetry, so these are coming around. So this one's solid, this one is a cylinder around the solid rod, and that's leaving a space in between. So if we draw a little bit of view of what's going on, it looks something like that. All right, and a little, some idea what's going on in here. Okay. And then that would do something like that. So here, RA is the radius of this one. The radius out to the inner surface of this one is RB. So water can fill these volumes. When we apply a potential difference between them, we'll get an electric field, and they point out that these radii are smaller than the length of the device, L. And the reason that's pointed out is because we want to assume that the E field between them is uniform. There's no complicating factors due to the fringing that actually occurs out here. So the field lines over here would actually fringe and get curved, but we're saying it's so long that that's negligible. We don't worry about that. So you get the E field like this, which means you're also going to get a current density going through the water. And it's that current density that we measure as a current I. That's the setup. So the first question then is, let's see, find the resistance of the water between the cylinders in terms of L, the length, the resistivity of the water, that's the thing we're interested in studying, and the two radii, RA and RB. So let's see. So our standard formula for getting the resistance from the resistivity is R equals rho L over A. And this applies anytime you have a uniform cross-section and it doesn't change. Right, so we often apply that to a cylindrical wire. That's what we usually do. Because the wire's cylinder, the wire's cross-sectional area is constant through the wire. Or we could apply it to sort of a wire with a square cross-section. And that would work because the cross-sectional area, again, is the same throughout. We did one problem, maybe it was in class, where we had sort of a wire whose area was changing with distance. And the way we were able to use this expression to get the resistance of this was to divide it up into little differential elements and do an integral. Right? So we know that this slice has a resistance dr, and this slice has a resistance dr, and this slice has a resistance dr. So we just add all those up by integrating, because we know that the resistance of a bunch of things next to each other that comes sequentially in the current, the total resistance is just the sum of the individual resistances in this case. So that gives us an integral. So we're going to do the same thing here. So let me draw it now cross-section the other way. Let's look down the bore of this device. So here is this surface, the metal surface of the outer ring that it touches, And here, I'll draw it kind of exaggerated small, is this surface, the surface of the inner rod. So what we have to do is figure out, to set up this integral, we have to figure out how can we imagine little surfaces that add up as little differential elements dr to give us the entire resistance. We know we're going from this surface out to here, so the symmetric thing to do would be to think about little differential rings, little differential concentric cylinders like this. Okay? So this is just a little differential cylinder, and we can actually apply this now because we're saying it's small and its area, its cross-sectional area doesn't change. It's just a teeny little piece. As we go from here to here, that area changes a lot, but a teeny little section, it doesn't change much at all. So we want to figure out what is the dr from that one. Because when we have that, we know that it's going to also, we'll have it for this one and this one and this one, and then down here to this one and this one, and we'll sum them up in an integral. Okay. So dr is what? Well, it's rho L over A. We just have to do it in terms of differential variables. Well, rho is a constant. No matter which of these concentric cylinders we're doing, all the way from this surface to that surface, rho is the same. So I don't have to worry about rho. Let's see. L. What is L? So it'll help us to unwrap this cylinder and kind of draw it this way. So let's imagine then that we took this little differential cylinder shell and unwrapped it. Then it's going to make what? It's going to make basically well, not a cube, but a rectangle that has some width to it. So the length around here depends on what radius you're at. Right? So we're going to do this integral over radius. So this length is the circumference of the circle at that radius. So it's 2 pi r. All right. And our thickness is just dr. And we have to remember that this is going down the length L. So I'll draw in heavy perspective here, L. And we have to remember the direction of the current. The current, we're saying, is going through here. So the current really is going like this. The current's going right through it. So now, let's apply this. Rho L. So in this case, what is L? L is this distance that we're going through. L is dr. And what is the area? The area is big L in this case, the length of the device times 2 pi r. And that's how we get it. So that's dr. Now r would be the integral of that from what? From RA all the way out to RB. Integral from RA to RB of rho, let's keep the constants over here, rho L, rho over 2 pi L, dr over r. These can come out of the integral. It's really just the integral of dr over r from RA to RB. The integral of dr over r is one of the standard integrals that you just memorize or keep in a table, and you get that this is rho over 2 pi L. Integral of dr over r is natural log of r. Natural log of r, but then we're about to evaluate it from RA to RB. So it's a natural log of RB minus the natural log of RA. When you have the natural log of two things subtracted, it's equal to the natural log of the ratio. So I'm going to skip one little natural log property and jump to that. So that's the same as evaluating this from RA to RB. You just do the whole integral. So that's R. That's actually, and that's the answer to part A. That is the resistance of the device as a function of things that we know about it. Its size, and the resistivity of water. Also, that is pretty much a standard resistance expression anytime we have two cylindrical surfaces, two concentric cylindrical surfaces. So if you look in the book, this is actually done in one of the examples. So one way to do this problem is just to recognize that this is a standard concentric cylindrical shell problem, and part A just say, well, we know this. This is given in the book, or this is a standard resistance formula. But I wanted to walk through it because it's a useful example of setting up an interval. So now, part B gets to the real question of what does our data mean? So let me just erase to make room our cross-sectional part here. And let me just erase this, and we will do part B. Part B asks, how do we get the resistivity in terms of things that are given, things that we apply, things that we measure. So what that means is, remember, we're applying a voltage here and we're measuring current. So we're going to apply Ohm's law to this thing. We're saying that the water basically obeys Ohm's law. So we apply delta V, we measure the current, and the relationship depends on the resistivity, the resistance R. So we can now write that delta V equals I times rho over 2 pi L natural log RB over RA. And if you want the resistivity, all you do now is just solve this for the resistivity. Rho equals what? Equals delta V times 2 pi L, bring that over here, bring that up there, and then divide by I, and the natural log of RB over RA. And that's actually the answer to part B. Because that's how you can get, when you throw this down in the ocean, you apply a delta V, you measure a current, and these are things you know when you built the probe. So that's the answer to part B.